In my last two examples, I am just going to be interpreting two free body diagrams. And the idea is here to reinforce that there's a common notation that you should be using so that whoever looks at your free body diagram knows what you're actually communicating. So here's a free body diagram on the left. Let's try to figure out what the situation is. So let's see. This is my normal force. That means that I have an object on a surface. This is my gravitational force, which just means that my object is, say, near a planet or on a planet. That's fine. Now I see that I have a kinetic friction force. So this is friction, and in particular, it's kinetic. So that means that I know that it's moving, at least with respect to the surface that it's on. And I see down here that I have a net force to the left, and so that means that it must be accelerating to the left. So, what might this look like? Well, one thing that this could be, we've already seen, right? This could basically be my book on a surface with a velocity vector to the right and an acceleration vector to the left, and we would say that my book is in fact, if I do a little motion diagram, slowing down. We have V1, we have V2, we have V3, and then we have stopped. So this would be my motion diagram for my book sliding, which is this free body diagram. Now, there are some other things that it could be that are a little more complicated to draw, but the point is here that I can look at it and immediately come up with a situation. Do I know it's a book? Well, no, it could be like a cat, for instance. But the important thing is we see, okay, it's an object that must be sliding to the right because kinetic friction is acting to the left. It must be decelerating because the acceleration vector must be to the left. Now, the other thing that I want to point out is that if you just looked at the motion itself, you might say this is a one-dimensional problem. But it's not. You have normal force and gravity. So that's one reason why it's always helpful to draw x and y and to not just make the assumption from the beginning that it's a one-dimensional problem. Okay, now this one's a little more complicated. We can see that the axes are tilted. So tilted means that this is on some sort of ramp. The other thing, to be very honest, I picked these free body diagrams slightly randomly, so I haven't actually thought through what these are. I am explaining this in real time without any forethought whatsoever, I promise. So we see that it's tilted. What else do we have? We have a normal force, which means it's on a tilted surface. We have a tension. Ooh. And again, tension is frequently abbreviated as capital T. I sometimes do it as F sub T to remind myself that it's still a force. Either one is fine. And we then have gravity. Good old gravity. And then my last force here is again friction. And note that it is kinetic friction. So we have kinetic friction and we have a net force which is downwards and to the left. So let's try to think through this. What could this be? So I'm not going to draw a motion diagram first. I'm going to try to draw a sketch. So I have some sort of ramp, and I'm going to put an object on my ramp. And let's say it's some sort of box. Okay, so by putting a box on my ramp, I've dealt with a couple of things already. I've dealt with gravity. Gravity's taken care of. And I've dealt with my normal force. Great. But now I need to cause that tension. So I have a rope. Okay, cool. Ropes pull. So my rope is being pulled that way with my force of tension. Okay, next I have kinetic friction. So I know that this is some sort of slightly rough surface. It isn't just ice. That's fine. And note that kinetic friction is acting, I would say, up the ramp. So if kinetic friction is acting up the ramp, this opposes the motion. So it must be sliding down the ramp. So if, oh, sorry, that technically shouldn't be V naught since it might not be constant. So we'll just say V. Okay, so it's sliding down the ramp. Since it's sliding down the ramp, kinetic friction opposes the motion which acts up the ramp. Lastly, we see that F net is down the ramp. And that means I can say that my acceleration is down the ramp, which that technically should have been parallel to the ramp. You get the idea. So our situation is that we have a block pulled down the ramp by a rope, and it is accelerating downwards. So even though there is kinetic friction, the friction isn't slowing it down. There is enough tension in the rope that it is speeding up as it goes down the ramp. Now that I have that drawn out, I can draw the motion diagram, which I technically could have just from the F net. So my motion diagram is that it starts up here with a lower speed, and then it accelerates downwards. So I have V1 up here, and then I have V2, V3, and V4. So the motion is still in one dimension along the ramp, but we have forces in all sorts of directions, and we have an acceleration vector, which is down the ramp. So again, good notation can communicate a lot, and whatever the last piece of information that I can figure out is whatever angle this theta is this angle. And earlier I showed the trigonometry that you would use to make that argument. So my hope is that this is clear, and again, by labeling what these forces are using fairly standard notation, and in an earlier video I introduced good notation practices for these, you understand what's going on. Even though we haven't talked in detail yet about how to calculate kinetic friction, just by knowing the direction, you know something about the velocity. So hopefully this has been clear. Again, I just want to keep stressing that free body diagrams are important before you do any sort of calculation. Okay, just to quickly summarize, you should draw free body diagrams anytime you are using a force model. So we'll talk a little more in the next chapter, in the next sequence of videos, what our two force models are. There's really just two different ones, but anytime you're using forces, there should be a free body diagram. Next, make sure that you're labeling your net force off to the side, and all other forces from that central point, which represents your object. So make sure that you're only using forces. Don't label a velocity, don't label an acceleration from that object, that point representing the object. And make sure that F net is off to the side. If F net is 0, make sure you explicitly write that down. You want to make sure that it's clear both to you and to me that you've gone through the time to figure out that net force is 0. Next, make sure that you've clearly labeled your forces with good notation to denote what they are. F1, F2, F3, F4, that's only good if you, for instance, have 4 different ropes or 4 different people that are pushing. When you have kinetic friction, normal force, gravity, use notation to make it clear that that's what they are. Finally, make sure that you have coordinates labeled and that you're using them. Carefully determine your force directions. If you can make some arguments about specific angles, do that. So again, at the very beginning I went through that tactics box of how to do this. Please feel free to come back to this and practice since free body diagrams are so important.